This is going to be part 1 of Euclid Book 4, proposition number 12. And the reason I'm going to put this in several parts is due to the fact that there are so many details to this thing that it may take me more than one video to explain it all. Alright, so we're going to go slowly here. What Euclid wants you to do is he wants you to draw an equilateral and equal angular pentagon. He wants you to circumscribe it around a circle. Well, obviously, if you're going to circumscribe something around a circle, you've got to first have the circle. So we're going to draw a circle A, B, C, D, and E. Okay. Then the next thing we're going to do is we're going to go back to Euclid Book 4, Proposition 11, where we actually drew an aesthetically pleasing triangle. This is a triangle that has two angles of 72 degrees and the other angle at 36. If you remember that from the last proof, you'll know what I'm talking about. And you have to draw this to acquire point C, point A, and point E. Once you do that, you have to continue on with that former proof because you then have to acquire points B and points D. Okay? Once you've acquired points A, B, C, D, and E using the aesthetically pleasing triangle and the rest of that Euclid proof of Euclid 411, then what you're going to end up with is 5 circumferences that are going to be exactly equal in size. The distance between points A and B on this circle are exactly the same as the distance between points B and C. Okay, so circumference AB is equal in size to circumference BC, and circumference BC is equal in size to circumference CD, and so on and so forth all the way around. So you have circumference AB equals circumference BC equals circumference CD equals circumference DE, and finally circumference EA. See how detailed this thing is getting already? Okay. Now, we have to draw 5 tangent lines. And the first one we're going to draw is GH, and we're going to draw it through point A. And then we're going to draw HK, and it's going to be drawn through point B, and so on and so forth. You have KL, it's going to be drawn through point C. You have LD, which is LM, which is going to be drawn through point D, and you have MG, which is going to be drawn through point E. Now, I know I didn't do this exactly right. I am sorry about that, but if you do it exactly right with the most precise tools, you'll get this. Okay? Now, we have to find the center of circle A, B, C, D, and E. To do that, we have to go back to Euclid Book 3, proposition number 1, and when we do, we find point F. So far, so good. Now, we're going to draw a line from FC, from point F to point C, and this line FC is going to be perpendicular to line KL. Here's line KL. So we're going to draw FC perpendicular to KL, and you can go back to Euclid Book 1, proposition number 9 if you'd like to find out how to do that. Fine with me. Anyway, we now have to establish that certain angles are 90 degrees. Well, what's FKC? Well, I'm sorry, FCK. Well, FCK here is 90 degrees because this line is perpendicular to this one. And FCL, same way. This line here is perpendicular to this one. Alright. Now what about FBK? Well, we drew a line from point F to point B that was perpendicular to KH. And so line FB is going to be perpendicular to line KH. Therefore, angle FBK, well, here's F, here's B, here's K, there's a 90-degree angle there. And FDL, well, let's see. We have F and D and L. What we have done here is we have drawn a perpendicular line from point F to point D. Okay? We drew this line from point F to point D. It is perpendicular to LM, so that makes angle FDL automatically 90 degrees. Whew. So far, so good. Now, we already know that FK is if you were to draw a square, okay, and this goes back to the Pythagorean theorem. This goes back to Euclid Book 1, proposition number 47. You have line FK here. If you were to draw a square with each side of the square, if you were to draw a four-sided square and each side of the square was the length of FK, then the area inside that square, and go ahead and draw it. You will see for yourself I'm telling the truth on this. Okay? So, if you have a square, and each side of the square is the length of FK, then the area inside the square is going to be equal to the following. Hang on just a second here. Alright. We have FC here. If you were to draw a square, and each side of the square was to be the length of FC, then you'd have that area. Now you're going to add that area to some other area, okay? And the other area is CK. Okay, so if you were to draw a square, and each side of the square was the length of CK, then you would take that area there plus this area here, and if you did that, you'd have the area of this one here. And that's by Euclid Book 1, proposition number 47. You can come up with the same thing with FK. See, here's FK here. And it's going to be equal to FB plus BK. Okay? Again, if you were to draw a square and each side of the square was the length of FB, and then you were to draw another square and each side of the square was the length of BK, you would have two areas, two square areas, and it would equal the third one over here. Okay. Now, we know that the square areas of FC and CK, well, here's FC and here's CK. These two areas right here, if added together, would be the same as FB and BK. These two areas right here. And I'm talking about drawing the squares as I described to you a little bit earlier. Okay? Now, if FC and FB are equal in length, which they are, see FB and FC, okay, they're equal in length because all radii of a circle are equal, then the square on FB and the square on FC are going to be equal in size. You say, well, what are you talking about? Well, if you were to draw a square and each side of the square was to have the length of FC, and if you were to draw another square and each side of the square was the length of FB, then the area inside of this square would be the area inside of this square. Okay? And that makes the square on CK equal the square on BK. Well, here's CK here, here's BK right here. You see how this is getting really detailed here? Alright. And if the square on CK and the square on BK are equal in size, then that makes line CK equal line BK. Alright, and we've already established that line FB and line FC are equal because already I have a circle are equal. And FK is equal to itself, as you can see here. Well then, what you have are two triangles that have three sides equal in size to each other. Okay? And if this triangle is equilateral to this triangle, then what you also have is BFK equaling KFC. Well, where's BFK? Well, here's B and F and K. This angle right here, and it is equal to KFC. This angle here is equal to this angle here. And we can go on to say that BKF, this angle right here, is equal in size to FKC. FKC, right down here. And that's where I'm going to leave off at this point. And I will tell you more in the next video, so stay tuned.